Hi guys, we're doing 8-2 sine and cosine. I want to remind you of this right in front of you. When there was a number next to the function that used to vertically stretch or shrink the original graph. This will happen to the sine function and cosine function. Remember also that if c was negative, then there is a reflection of the graph across the x-axis. So if we look at y equals sine x, versus y equals 2 sine x, c in this case is 2, you'll see that y equals sine x is in yellow right here, and y equals 2 sine x will be stretched vertically up to 2. So the amplitude will actually change. So I'll go up to 2 instead of just to 1, and I'll go down all the way, again down all the way to 2, again. My graph doesn't look great. Let me fix it. So I tried my best. The zeros didn't change. All the zeros are the same. The only thing that changed actually is the amplitude. So the amplitude is now, instead of 1, it went up to 2. So the amplitude is actually now 2. The period is still 2 pi. So all the values are basically doubled. All the y values are doubled. So the x values stayed the same. Let's look at another example. So if we look at y equals negative half cosine x versus y equals cosine x, we'll see that because c was negative, there is a reflection of the graph across the x-axis. So instead of having the point at 0, 1, where normally cosine is, now it's reflected down the x-axis, and also because now it's at negative a half, the amplitude is just at 1/2, so it's going up to a half, going down to negative 1/2. So instead of going up all the way to 1, it actually now is reflected and shorter, because c actually did shrink the graph. I hope this helps. Let's keep going and do more examples. Let's look at c again, but in this case it's in another position. So c is not in front of f of x all the way at the beginning. It's actually a coefficient of x. So it's right next to x. In that case, it does a horizontal stretch or shrink, versus, as we saw before, it was a vertical stretch or shrink. So in the previous case, where c was in front of f, there was a vertical stretch or shrink that affected the amplitude. In this case, there is a horizontal stretch or shrink which will affect the period. So in this case, I'm looking at y equals sine x in yellow, just the regular y equals sine x. And we know that the zeros are 0, pi, 2 pi, and then plus or minus pi n. So every pi. And the period is 2 pi because that's when the graph finishes a full cycle, and then the pattern repeats. Now, when the coefficient is in front of x, really what that does affect, and is very visible in the graph, and it's like a shortcut, is the zeros. So now, instead of having just the regular zeros, 0, pi, 2 pi, it's going to be doubled. The amount of zeros are going to be doubled. And that's how I think I graph it, and most people do it fast, graph it like that. They just think of the zeros. The zeros are doubled. So really the graph will shrink because it will go up and down really, really fast, and all the zeros will be doubled. So we'll have more zeros. Now I want to calculate those zeros to show you algebraically. Now I know that in the regular sine x graph, sine x equals 0 when x is 0, pi, 2 pi. But now what if sine 2x is 0? So I want to calculate the zeros algebraically. So I'll do the same thing with the angle theta, which is in that case instead of x is 2x. But I still for 2x have the same values for that angle, whatever it is. All I'm going to do now is to divide by 2, and then watch what happens. So if I divide all the zeros by 2, I get 0 pi over 2 instead of pi, pi instead of 2 pi, and then the pattern keeps repeating. So if I want to graph this, I will notice that actually my zeros are now at every point marked on the x-axis. So now if I look at the graph, I'll see that the zeros are 0, pi over 2, pi. So really, instead of being 0 plus or minus pi n, it's now 0 plus or minus pi over 2n. And that's how it's affected. Now the period is also affected because you see the graph cycles really fast. And if we notice that yellow graph was actually cycling from 0 to 2 pi, that's one full cycle going up and then down and then back to the x-axis. Now I'm cycling that same cycle just to pi. So they say, you know, to calculate it algebraically, you can do 2 pi divided by that coefficient, which will give you pi. Or you can observe the graph and you'll see it's from 0 to pi. Now that coefficient, we'll call it b from now on. So instead of c, we'll say it's the b value. So we'll just call it b from now on. So we'll say that the period is now pi, because it's 2 pi divided by 2, where 2 is b, and so we get pi for the period. And if we look at the graph, you'll see it very clearly. It's one full cycle. Now, if we look at another example, y equals cosine half x, you'll see that normally cosine x will go from 1 all the way down. When it comes to pi, it's at -1, and then all the way up, and that's one full cycle at 2 pi. Now, what happens with that coefficient? Well, that coefficient is less than 1, and it's going to lower the number of zeros by half. So instead of doubling the zeros like the other example, now we're actually lowering the number of zeros by half. And again, we'll look at it algebraically to determine now the new zeros of the graph, because that coefficient is the coefficient of x, and it will affect the period, which is the x-axis. So originally, cosine x was equal to 0 at, or when x was pi over 2, here on the yellow graph, the original cosine x, 3 pi over 2, and then every pi from there forward and backwards. So I'm doing the same thing to cosine half x. So I'm saying that, you know, half x is at pi over 2, 3 pi over 2, because that's theta, it's the same theta. But because I have a coefficient, I'm just going to multiply them all by 2. And now x will be equal to pi, 3 pi, and then plus 2 pi n. So every 2 pi, there will be a 0. Now, I know that I see it in the graph. The graph cycles one full cycle between 0 and 4 pi. And again, to figure that out, it's either you do it algebraically, so you do 2 pi divided by b, which is a half, or you can just observe the graph. It's always helpful to know both, how to figure out the period on the graph and just algebraically, because we're going to be creating equations based on the graph. It's actually fun. So you'll see that the period, or the one full cycle of the graph, is at 4 pi. That's where it stops. And we can see it right there in black, y equals cosine half x. All right, let's keep going. So if we look at this lovely cosine graph right here, you'll see that there's some changes that happen to it. So first of all, I know that the cosine graph will keep going, so it's not that it's going to stop right here. Later on, we'll know that we can do a shift, but right now, you know, when you see something like this, you normally know that cosine graph starts at 0, 1, and then down and up again. So over here, there's like a big difference. You know, it's not starting at 0, 1, it's actually starting at 0, -2. So that starting point will help you identify what happened to the amplitude and figure out what the amplitude is. So again, this is supposed to be my starting point for cosine, but now it's down here on the y-axis. So the amplitude looks like instead of going up to 1, it's now going up to 2. Instead of starting at 0, 1, it's now starting at 0, -2. So there's a reflection also. So that means that my coefficient is of the function is actually negative, because there happens to be a reflection. Looking at the general form the amplitude is always the first number, the first coefficient, and then b is my period changer. So I have negative 2 is the first number, because 2 is the amplitude, and then it's negative because there happens to be a reflection across the x-axis. So instead of starting on the positive y-axis, now starting down on the negative y-axis. So the x-axis acts like a symmetry line. Now I want to look at b. So I want to know what happened to the period. So obviously the period doesn't stop at 2 pi, because we see from now 0 to 2 pi, that's half a cycle. So looks like it's going to go all the way to 4 pi, because I'm at half a cycle at 2 pi. Another way to figure out the period is if you would look at the entire graph and just figure out the length horizontally with the x-axis. So I have, negative 2 pi over here on the negative direction of the x-axis, another positive 2 pi over here, so I have a 2 pi distance on the negative direction and a 2 pi distance on the positive direction to complete a full cycle of cosine. So I have a 4 pi period. So that's the equation for the period. We used it before in the previous example. So we say 2 pi over b equals the period 4 pi. In this case, it's reversed. In the previous example, we actually had b, and we wanted to calculate the period to see what effect did the b have on the period. In this case, we're actually observing the period from the graph. So then we say 2 pi over b equals 4 pi, and then we solve for b, which is that number that we're going to plug in next to x. So we multiply by b, then divide by 4 pi, just a shortcut. These guys switch places. And then we have 2 pi over 4 pi equals a half. So my coefficient is actually a half. And that's the equation for the graph. Let's look at another example. So we have y equals, again, the amplitude, sine or cosine. In this case, we'll do sine. And then b, x. So we have the amplitude is apparently going up to 3, down to negative 3. There's no reflection there, so the amplitude is positive. The period is actually going to 4. So if I want to calculate the period, I need to remember to do 2 pi over b equals the period. So the graph cycles a full cycle from 0 to 4. So if these guys switch places, I'll know that b is pi over 2. 2 pi over 4, or pi over 2. So this is the coefficient next to x. I hope this helps. Tomorrow in class we'll do a little bit more tomorrow, so don't stress out. If you have any questions, you'll ask me tomorrow in class. But I think now you have a general idea, and you can do your homework. So you can check my Connect for the homework. It's page 305, 1 to 26. All right, good luck.